Now, to understand this lesson, we need to do a bit of revision of vectors in 2 dimensions. That was done in year 12 extension 1. So in 2D, what we had is the plane. So say, okay, so this is the x-axis, this is the y-axis, and we create a unit vector, which is a vector I, vector I. And then on the y-axis, there is a unit vector called the vector j. And say, for example, you have a vector here, which is the vector u. This is, so basically that's 4 and say 3. So we say, well, u is equal to 4 times the vector I plus 3 times the vector j. Now in 3D, it's pretty much the same, but there is an added level of complexity because we need to represent on a 2D plane, which is this screen, the 3D space. So, okay, so in that case, what we're going to do is we're going to show the x-axis here, the y-axis here, and the z-axis here. And here along the x-axis, so they are all at 90 degrees, okay. Along the x-axis, there is also the unit vector I. Here along the y-axis, there is a unit vector j. And then along the z-axis, we define a unit vector k. Now, it's important to represent it that way and not say, oh, vector y here, and then the x here, and then unit axis here. This doesn't work. Now, it could work. The problem is this led to problems in physics because 3D vectors are used in physics, particularly electromagnetism. And that leads to contradiction. So we cannot choose this orientation. We need to stick with x, y, and z oriented that way. And so if, say, so basically it's rotated from x towards y and then y towards z like this. Now, sometimes, to remember that, people use, I'm just going to try to represent it with the hands. So this is basically your fist and your fingers here. So basically a hand, and then we rotate it like that. And then this is the z-axis. So we rotate from x to y, and not the opposite, your right hand. Right. It's probably the best way to remember it. Anyway. So, coming back to the example of the z-axis here, the x-axis here, and the y-axis here with the unit vector I, j, and k. So obviously that's going to be very difficult to represent, but say if I have a vector u here, and this vector u is just going to be, let's project it here. So say that's going to be 2, and it's going to be 1, 2, 3, 4, 5, 3, 4, 5, 6, okay? And then here it's going to be what? 2. So we say, well, basically the vector u is equal to 2 times the vector I plus 6 times the vector j plus 2 times the vector k, which sometimes is written 2, 6, 2, or also written u, u 2, 6, 2. Two different ways of writing it. Now, if I want to calculate the length of the vector u, well, that's Pythagoras in 3 dimensions. So that would be 2 root of 2 square plus 6 square plus 2 square, which in that case would be what? 4 plus 36 plus 4, so that's the length of u is root of 44, which can be simplified. I'm not going to do it. Then basically for two vectors u and v to be equal, we must have u, the x component of u must be the same than the x component of v. The y component of u must be the same than the y component of v, and the z component of u must be the same than the z component of v. So in that case, the two vectors are equal. Also, so that's one statement. Two vectors u, which is the same as ux, uy, uz, and v, vx, vy, vz are parallel if they exist lambda belonging to R such that u is equal to lambda v, because basically they have the same, this is vector u, and this is vector v, and so they are just basically in the same direction, but they have slightly different length. Note that if they are opposite directions, say so if v is like this, they would also be parallel, but in that case lambda would be negative. That's it for this lesson.